So let's cover the agenda. I've covered the introductions, and I'll just now describe briefly the variation design challenges, and then we'll have a description from Jason on the TSMC AMS reference flow and what they're doing within TSMC to support variation-aware design. And then I'll go through the subflows, the advanced PVT subflow and the advanced Monte Carlo subflow that we have within the reference flow. Finally, I'll go through and talk about a few customer successes using Solido tools, and then summarize with closing comments and then questions and answers at the end. One thing that we see as we go to smaller and smaller geometries, obviously the drive to smaller geometries is to get higher levels of integration, lower costs per function, but as you drive to smaller geometries, we're actually starting to see that variation effect is becoming a very important consideration. At 65, arguably 65 nanometers, you could design around the variation effects, actually maybe guard banding a design and follow your prior flows for design development. But as we move to smaller and smaller geometries, such as at 28, and then as we move to 22 and 20, it's becoming mandatory now to be able to do variation effect analysis and understand exactly the impacts that your designs will have. Now, we did a survey earlier this year, an independent survey, and 65% of engineers in that survey reported that variation effects will actually be their top concern and their top priority for analysis in the next 2 years. So let's talk about the types of variations to consider. On the left-hand side, we have the operational. This is more the effects of variation around the design, such as supply, voltage, temperature, different loading conditions. If you're designing IP, then you may actually have different conditions of how that IP should function in different situations. On the right-hand side, you have the fabrication variation. Global variations have been historically analyzed through corner-based models. But now, as I mentioned, as we go to smaller and smaller geometries, the local effects are now starting to be almost as big as the global effects as well. And they have to be done or taken into account with Monte Carlo-based tools. The third challenge is layout-based implementation effects. There's the physical parasitic effects that people have been dealing with for many years. There's also the power integrity connectivity effects for your supply domain that also has to be taken into account. And the more recent phenomenon is the layout-dependent effects, where the actual devices themselves will change in their electrical characteristics as you place them, and also depending on their placement relative to other devices and other diffusions. All this represents a huge number of challenges that the designers have to face. So they can either run less simulations in order to meet a deadline, in which case there's less predictability as to the quality of the design over those challenges, or they can actually do more analysis and then run the risk of increased validation costs. This represents a fundamental challenge for the designers, and they have to choose between over and under designing. It's difficult to find that optimum design between the two extremes. So now I'm going to hand over the presentation to Jason, who's going to discuss the TSMC AMS Reference Flow 2.0.
Greetings to all the audience on TSMC Solido webinar. This is Jason Chen from TSMC Design Methodology Service Marketing. Today I'm presenting variation-aware solutions in TSMC's Analog Mixed-Signal Reference Flow 2.0 and how we collaborate with Solido to provide the solutions for our mutual customers. Here's the outline of my presentation today. I will start with a brief descriptions of the challenges that we're facing at advanced nodes. Before I present our analog mixed-signal reference flow and how Solido's solutions helps, I'd like to give the audience a general overview of TSMC Open Innovation Platform, because that provides a background of this collaboration between TSMC and Solido for this webinar. How AMS reference flow was created, why and what it fits into TSMC ecosystem, and serve the needs from our end customers. Then I will present how Solido's advanced Monte Carlo is applied in AMS reference flow 2.0. As more and more designs are getting into advanced nodes, designers are starting to find bigger challenges to overcome more and more design variations that are not only coming from foundry process and devices. There are too many other variations that designers have to consider. The designers used to have the luxury to enjoy enough margin in their design in order to budget in those variations. But now in advanced nodes, the design voltage swings are much smaller, as well as the smaller ranges of other electrical parameters. Therefore, the overall design margin is much smaller, especially for those designs, sensitive design, such as power devices, high speed, are more sensitive to variations and require consistent statistical verifications. Designers are often use traditional Monte Carlo to reasonably budget the variations by running different process, voltage, and temperature corners. It used to be a good choice for calculating the histograms and the standard deviations, but now designers are also starting to reach the upper limit of Monte Carlo because the trade-off between the runtime and accuracy is getting tougher and tougher to reach. Besides, Monte Carlo is not easy to be used for debugging the circuits because it failed to identify the sensitive devices in the circuit. From the physical layout standpoint, the layout-dependent effects are getting more and more significant in more advanced nodes, which are highly dependent upon users' layout placements. The same for the interconnect RC and the EMIR jobs are also affecting designers' circuit at a much bigger scale now. TSMC from foundry standpoint introduces a concept of open innovation platform based on the TSMC's solid foundation in process technology. We work with EDA partners, IP partners, and even the Design Center Alliance partners to collaborate all the innovations to establish the ecosystem in order to provide a complete design solution to our end customers. Through this open innovation platform, we leverage resources through the early engagements in tools, IP, process design kit, flow, and methodology, and also the device services. We collaborate to resolve those issues with enhancements in EDA tools, flows, and methodologies. The outcome is smaller investment for our end customers to handle all the bigger challenges at advanced nodes, as we described earlier. TSMC announced the readiness of the 28 nanometer design ecosystem is a good example of the outcome of the open innovation platform. Analog mixed-signal reference flow is one of the products from open innovation platform. The traditional design flow of the design, simulation, layout, extraction, then iterate to resolve the issues in the circuit designs and the layouts. In the meantime, need to juggle all the variations throughout the design flow. Analog mixed-signal reference flow 2.0 enables the designers to loop between the design specs and the layouts with much smaller iterations, and to resolve the layout-dependent effects, RC, EMIR, at the same time. The idea is to run variation analysis on designers' circuit spec to derive all the electrical constraints. Then TSMC converts them to physical constraints so that all the corresponding EDA tools can handle those LDE, RC, and EMIR later on during the mini-loop iterations between the schematic and the layout. In order to get this flow into reality and achieve the purpose to minimize the design iterations, the initial variation analysis plays a very critical role to trade off between designers' circuit spec and all the hidden variations from all over the place. Therefore, we look into Solido's advanced Monte Carlo methodology. It contains 4 different major stages, which are analyze, identify, fix, and verify. Even though there are some very generic stages to approach and solve the problems, Yet it does contain very unique algorithms to help remedy the disadvantage in the traditional Monte Carlo executions. In Analog Mixing or Reference Flow 2.0, we have applied advanced Monte Carlo in different design test cases. During the analysis stage, it was able to use the 45 simulations to verify the design not meeting the 3 sigma requirements, while the traditional Monte Carlo requires 200 simulations. Then we run through 3,400 simulations to verify the designs meeting 3 sigma's target, while the traditional Monte Carlo needs 3 times of the simulation runs than the advanced Monte Carlo. It easily extracted the 3 sigma corners to identify the sensitivities, then suggest the most probable design improvements to go through the iterations, then to fix the sensitivities. At the end, we verify the yield using different sigma ranges on various design test cases. High sigma Monte Carlo verification was used for high sigma applications to greatly reduce the number of samples that traditionally need for high sigma applications. As the verification results show, they are accurate based on the negligible error probability. High sigma Monte Carlo were scaled to 160 process parameters with no problems. Next slide is to show the sample results from the charge pump test cases that was applied with the advanced Monte Carlo methodology. As you can see the differences, the yield shows much better improvement with all this, and also the 3 sigma output results are also much more centered with a tighter distribution. As a summary of my presentation, the audience can see this as a successful example of within the scope of the TSMC Open Innovation Platform. Knowing what are the challenges from process and the designs in advanced nodes, TSMC collaborates with EDA partners at early stage to minimize their investments during the iterations of trial and errors. TSMC Analog Mixing or Reference Flow also provides a non-intrusive alternative to the traditional design flow. With Solido's unique innovation in variation analysis, it helps customers' designs, especially the ones that are highly sensitive to the variations, to improve the yield and centering with less Monte Carlo samples. In the meantime, there's no trade-off with the expected design accuracy.
Thank you, Jason. Now I'd like to talk about the advanced PVT flow, but before I start, I'd like to just give an overview of Solido first. So Solido has been around since 2005 and has become a recognized leader in managing the impact of variations on your design. Now, as Jason mentioned, there's a number of steps that you go through: analyzing, identifying, and fixing your design, and then re-verifying. And these are steps that engineers have been using for many years. Now, what Solido provides is the ability to improve efficiency in each of these steps. So in the case of analysis, we provide technology to reduce the number of simulations you need to do to run it through your design to find out what your design can and cannot do. In other words, we're able to reduce the number of simulations for the same level of coverage. In the case of identifying electrical hotspots, we provide tools to help you understand what trade-offs to make, understand what design impacts there are for your design, and understand what specifically the devices that can impact your design to improve its overall performance. And then fixing, we actually provide the technology for you to quickly see how each change impacts on your design, so you can actually compare the before and after, and as you go through a multi-step process, you can actually see how each step impacts your design, and in fact you can even go back a step. Now, I talked about the variation effects being a big challenge at 28 nanometers and even smaller, but the Solido solutions have actually been in use for a number of years and are available and in use for customers at 130 nanometers as well. So the Solido Variation Designer cockpit has a number of tools at the top that we plug into. We call them packages, and each of these plugs in a set of capabilities. But within Variation Designer, we provide a number of interfaces. There's the PDK interface, which interfaces us to all of the PDKs that you get from TSMC. From a flow perspective, we integrate into the Virtuoso flow at the 5.1 and 6.1 level, but you also have the option to interface at a netlist-based flow as well. One thing that's important for us is to be simulation independent, and so we interface to all of the most common simulators for electrical analysis. Now I'm going to talk specifically about the PVT flow, and there's a number of capabilities we offer in this space. As I mentioned, our whole goal is to reduce the number of simulations you need to increase the level of coverage that you have per simulation. So in the case of design debug and understanding which are your failing corners, we can debug those corners and find those corners 20 times faster than trying to run through all the corner set. And once you go through full verification, we're even faster in that verification process as well, so you don't actually have to run all of your verification corners. But we're able to give you the full coverage with 8 times efficiency in overall productivity of the tools. We're able to identify the failing corners very quickly, and this is important because this feeds into the rest of the flow for design debug. Fail corners are always a problem. If everything passes, then everything's great, but if things fail, that's when the challenge really starts. And we provide the tools to help you quickly explore what your design can and cannot do, what design changes you can make, what trade-offs you can make, and this provides a 30% reduction, and this actually is a reported number by our customers, in the overall design debug phase. And as I mentioned, as you go through each design change, you can keep track of the history of those design changes. So within the advanced PVT subflow, specific to the TSMC AMS reference flow, we are addressing a number of key capabilities. We want to provide more coverage with fewer simulations. We do this with a DOE-based technology, which I'll discuss in a second. And we want to provide, since we have all this analysis over corners, we can actually provide you some insights as to which are the key contributors of your environment variables. Maybe supply, maybe temperature. You can extract those corners and feed them into your analysis for determining which are the key design variables that contribute to that PVT variation. As I mentioned, we have a 30% reduction on average in the debug time for fixing your design across PVT corners. The specific technology that we offer within the TSMC AMS reference flow is included here. So there's the design of experiments, where we provide an orthogonal, fractional, factorial, and a sweep. You can actually do a deeper dive with sensitivity analysis, and as I said, there's actually other sensitivity analysis capabilities that we offer, and it's always across the worst case corners. We provide insights to help you understand how to optimize your design, but this is a manual optimization using the expertise of the engineer, and we provide insights and the analysis capabilities to explore your design. It's all through full interactive control. So it's taking the advantage of the expertise of the engineer and the expertise of Solido in running through simulations and presenting information. Okay, so now I'd like to talk about the PVT flow in the context of the Analyze, Identify, Fix. The first step is to analyze what you can and cannot do, what your design will or will not do in terms of your specification. So here you can see I've run through a number of corners. The green region represents the passing corners and the white region represents failing. So there are a couple of failures. This particular plot is showing you the sensitivity of your design to supply variations across corners. The next step is to extract the worst case corners, and then this helps us. So if you have, say, 200 or 300 corners, you can actually just extract the 3 or 4 corners which represent the worst case for design debug and analysis. You wouldn't need to do this if you have a design that works, but if you have to go through a debug phase, then this helps to make the process go a lot faster. The next step is simply to run a sensitivity analysis across the design changes that you think would have the most impact, and you can do this across all of your devices, and it's very quickly to run a sensitivity analysis, but this is again across all your worst case corners, and it helps you to filter out which devices are going to have the biggest impact and have the biggest contribution to a design change. Once you've identified your primary devices and your primary variables, then you can explore the design in much deeper detail. Here I'm just showing you a contour plot showing you the pass and fail regions of two devices as they're being varied. This helps you to identify potential fixes, and we help you determine which devices have the biggest contribution over your design exploration space. And once you've identified a fix, then simply you make the changes to your schematic, update your design, and then rerun the verification. But here, the verification is simply just running it over your worst case corners. So here, in this particular example, you can see that the updated version is now passing and is within the green region. So this represents the worst case corners. And so when we go through to full verification, you can clearly see that all of these corner simulations are now within the green region and passing. What recently has been released by Solido is to focus specifically on this last step. So we offer a fast PVT solution. This fast PVT solution has two basic components. There's the corner extraction, and that's primarily intended to give you a quick insight into where your worst case corners are as you go through design development and actually also within design debug. The next is verification. This is a much more rigorous analysis of your corner space, but again it's still more efficient. So whereas the corner extraction is typically 20 times faster at determining your worst case corners, the design verification will actually do a much more rigorous analysis, but still 8 times faster on average in terms of going through the analysis to verify over all the corners. All these methods take advantage of your distributed processing as well and leverage your compute farm. We do offer some levels of control, so you can actually even set a time limit or simulation limit to determine that, okay, I have to run my simulations overnight and I want to know what my best capability is by 8 o'clock tomorrow morning, and you can set a time limit and actually it will run through the analysis and run the worst corners it can find within that time limit. You can also set a margin limit as well, which allows you to have some level of flexibility over the tolerances that you define. Here's a video of the fast PVT application, but before I launch it, I'd like to just show the Variation Designer window that we're going to launch from. Now on the left hand side are all the different applications that you can plug into the Variation Designer window, and depending on which application you select, you have a different configuration in this center window to configure that particular application before launching. So for us, we're going to launch a PVT analysis, so it makes sense that you'll see settings to configure all the different corners over process and over all my different environmental conditions. Here you would also set your output specifications, your measures, your goals for each of the measures that you want to achieve. You can define the limits. Now if I look through all the different combinations of corners that I want to run, I find that I have 3,600 total combinations of corners. So we have, as I mentioned earlier, the three application options, which is fast PVT corner extraction, which runs quickly through using design of experiment technology to find the worst case corners. And then there's the fast PVT corner verification, which is a much more rigorous and conservative analysis that goes through and really works hard to make sure it finds all the worst case corners. Or you have the option of running all the combinations. So I'm going to start up the application now, and this will actually launch a new window, and then within that window you'll see that we have different sub windows, and I'll just let it start and then I'll just pause it here as it reaches 17 simulations. So what we're seeing here, and I'll just explain the window, is that for each measurement you have, like DC gain, phase margin, etc., there are two columns within each measurement. So the green region represents a passing region and the white region represents a failing. Now as you can see, through 17 simulations of 3,000 I've already found a failing corner. Now this is just one, so obviously there's going to be more, and as I go through the analysis it's actually going to take the predicted simulations and move them over to the actual simulations until there's a high level of confidence that all the predicted simulations are bounded within the ones we've already simulated for finding the worst case. So you'll see a progress as we go through this process. So I'll just restart it. So now we're running through the simulations, we're at 30, 40 and so on. And as you can see, the progress is increasing as the confidence increases that we've found all those worst case corners. So we have 5 measurements, so it takes a bit of time to actually find all of the corners, because some corners and some measurements themselves take a certain amount of time to actually find. So in this particular case, it took a total of 156 simulations to fully verify this design from the original 3000 that we started with. As a summary, the advanced PVT flow shows how you can use the Solido Variation Designer with the PVT Plus option to quickly find the worst case corners, find the most probable design changes to meet design goals across those corners, and validate the fix compared to the original performance. In this particular case with the TSMC reference design, we're able to show and find the worst case corners very quickly and actually find the failing corners 3 times faster than running through all the corner combinations. We're able to go through the full debug flow and improve the design performance by 40%. The right shows how each tool specifically is designed to support the Analyze, Identify, Fix flow with final verification, efficiently maximizing your design flow with the minimum number of iterations. As we push to process technologies, the amount of statistical variation increases to the point where Monte Carlo based analysis is moving from a nice-to-have type technology to a must-have technology. And to support engineers in this transition, Solido offers the advanced Monte Carlo flow for analysis for 3 to 6 sigma. So for 3 sigma, we offer the Monte Carlo package, which plugs into the Variation Designer platform. Now the key challenge for Monte Carlo analysis is understanding how many simulations to run in the first place. Now Monte Carlo Plus is quality driven, where the user only needs to define the level of verification they want to achieve, so for example 3 sigma. For actual Monte Carlo analysis, Solido offers the standard pseudo-random Latin hypercube modes, but also includes a statistically more efficient mode called optimum spread sampling, providing an average of 3x improvements in the result convergence. Similar to the PVT flow, you can generate worst-case corners, but in this case you would be generating statistical worst-case corners, say at 3 sigma. Then users can then design across those statistical corners with the same level of benefits in productivity, along with the ability to track all the design changes. With the advanced Monte Carlo flow, only the required simulations are run. So if a design is clearly not going to achieve the target yield, the analysis will automatically stop. Similarly, if the design is good, then only enough simulations are run to be able to prove that it meets the target yield. Because the analysis is quality driven, the results are inherently accurate, and the user can do deeper analysis on the biggest influences for their design to understand margins and trade-offs. If you have a failing set of corners, then you can extract those from the statistical distribution and then start doing a deeper dive into fixing and improving your design, as we discussed before with the PVT flow. The key technologies provided within the Monte Carlo flow are quality-driven Monte Carlo analysis, as I mentioned. There's no need to guess the number of samples that you need. There's the optimum spread sampling in addition to Latin hypercube and standard Monte Carlo sampling. There's 3 sigma corner extraction for fast design debug, and then impact analysis to understand the key influences on your design margins. This is all brought together in the design sense to understand the sensitivity across your statistical corners to find the most probable design improvements that you can make. Now high sigma Monte Carlo takes the 3 sigma analysis out to the 6 sigma realm. So high sigma Monte Carlo solution extends that level from 3 to 6, but that also means a lot more simulations or a lot more data points are needed. So for example, a target yield of 6 sigma needs approximately 5 billion samples to prove a 6 sigma margin to 95% confidence. Now HSMC adaptively determines which of the 5 billion samples to run to find the samples that represent the extremes of the distribution, or the tails. So running on average 1,000,000 times faster, taking advantage of your favorite simulator and also all of your parallelized compute resources. Unlike other products targeting 6 sigma, HSMC is capable of supporting up to 1,000 statistical variables. Similar to Monte Carlo Plus, High Sigma Monte Carlo will auto-stop once a level of quality is either proven or disproven. So HSMC achieves Six Sigma verification with Monte Carlo accuracy, since it's using the original Monte Carlo samples and an adaptive algorithm to select which simulations to run. So a Six Sigma verification can take typically 10 hours on a memory core, for example. Now in 2.7, which is our next release, we are actually taking advantage of multi-core and distributed processing to be able to cut that down significantly to just a few minutes. So since devices can take up to 10 statistical variables per device, it's important to be able to scale well. So far, HSMC has been tested up to 1,000 variables. So all the results are plotted, making it easy to verify the quality of the results generated. As before, Six Sigma corners can be created for use in design debug. The key features of HSMC are an adaptive algorithm that focuses attention on the tails of the distribution. Simulators are run on your favorite simulator, taking advantage of the multi-core and distributed processing capabilities. Now for High Sigma debug, we also offer QQ plots, which are available to help you debug the distribution and the characteristic shape of your design and the performance metrics, especially when they're non-Gaussian. And now we'll have a short video demonstration presented by Drew Plant, Senior Application Engineer for North America.
Traditionally, people have used Monte Carlo to validate design robustness. The limitation of Monte Carlo is that it takes too long to validate much beyond the standard 3 sigma, and is certainly much too slow to validate to 4 sigma or beyond. HSMC enables reaching out to 4, 5, and even 6 sigma. HSMC is accurate and has been used successfully by customers on several designs. Because HSMC samples are real Monte Carlo samples, it remains accurate and verifiable. This table compares the standard legacy Monte Carlo approach to two different HSMC runs. All three runs are for an SRAM bit cell design. Let's suppose we want to verify our design to 4 sigma. This requires on the order of about 1 million samples. First, we ran the 1 million samples using the standard Monte Carlo approach. It took 8 days and uncovered 0 failures. Next, we ran HSMC with the 1 million samples. Here's a time-lapsed video that shows that run. First, HSMC begins generating the 1 million Monte Carlo samples just like a normal Monte Carlo analysis. Then it simulates enough of the samples in order to gather information about the output distributions. Finally, HSMC concentrates on the tails of the distribution. It runs the tail samples until the probability that any failures have not been found becomes very low. Here you can see how HSMC has simulated the tails of the distribution, requiring only 531 simulations to do the step. It was therefore able to verify to 4 sigma, but took only 10 minutes and 15 seconds, compared with the 8 days required for standard Monte Carlo. 100 million samples would be clearly impractical with traditional Monte Carlo, which would take on the order of 800 days. We'll run the 100 million samples with HSMC. As before, in the second run, the samples are generated first, this time for the 100 million samples. Next, enough samples are simulated to gather information about the output distribution. Once this is completed, HSMC uses the distribution information to locate and run samples that are out in the extreme tails. With 5.3 sigma, the tails of the required distribution are further out. Several samples are identified by HSMC as being outside of the spec. Once again, a dialog box indicates that all failures have been found. From our 100 million sample case, HSMC identified all failures, 738 of them, and verified the design as being around 4.8 sigma. This operation took only 2 hours and 14 minutes. To summarize, HSMC is a fast and accurate method of analyzing and verifying high sigma designs.
So in summary of the advanced Monte Carlo subflow within the TSMC AMS reference flow, we were able to analyze the charge bump and validate that it wasn't going to meet the target specification, and did that within just 46 samples. We were able to generate 3 sigma corners directly from the analysis of the design, and then use those corners to improve or suggest improvements to the design to improve the overall yield. and then we ended up improving the yield from a 68% to a 99.7% or 3 sigma target yield, tightening the charge point variation by 50% in the process. We then used the high sigma tool just to show off the capabilities on the VCO to 4 sigma, going 200 times faster than it would typically take with Monte Carlo. Now PLLs are not typically analyzed to high sigma, so we actually incorporated some memory cells into the reference flow for that purpose. So the high sigma analysis of a sense amp to 5 sigma actually ended up validating 50,000 times faster than it would typically do with Monte Carlo. And then the validated bit cell that I just saw in the demonstration was actually 1,000,000 times faster than a Monte Carlo typically would take. Again, on the right hand side, we adopt the analyze, identify, fix, verify flow. Now I've given a very brief overview of what Solido is doing to improve a designer's control over variation effects. Now I'd like to talk about just a few customers who are using Solido tools in production with TSMC. So in the first case, Mohammed Aburama at Qualcomm used high sigma Monte Carlo in the verification of his memory design at 28 nanometer, presenting his 16-bit cell recently at DAC. The prior flow was to run a high sigma Monte Carlo and extrapolate the results to 6 sigma. This assumes the distribution is pretty linear, and most non-linearities actually appear near the distributions of the tails anyway, and so therefore would not be seen. In this example, he was able to use high sigma Monte Carlo to validate his designs was capable of meeting his 5.8 sigma goal with 1 billion samples, and running it within 3 hours. He was also taking advantage of XSpice across 100 distributed machines. Now with the new 2.7 release I mentioned growing faster, it will run in typically less than 10 minutes. The second case covers the experience of NVIDIA using Solido at 28 nanometer. Here, Tinku has used all of the Solido products to improve design validation in memory design, standard cell design, and analog I/O. Additionally, NVIDIA has worked with Solido to develop a power verification tool that plugs into the verification platform. The third example is the experience of Yun Chen at Huawei HiSilicon, who used the 2 flows presented today. So in the case of corner analysis, he was able to find the worst case corners within just 8 simulations, and then use the analysis identify fix flow to quickly improve the design in a single pass. On the statistical side, he was able to verify a design was not going to meet the target yield within 40 samples, and extracted the 3 sigma statistical corners for design debug. In addition, he was able to take advantage of key characteristics of the op-amp to help verify the performance of the full DAC linearity through that tight correlation. Now we've covered fairly quickly the overall Solido solutions within the TSMC AMS reference flow. So in summary, variation-aware design is a collaborative effort. The customer faces the ultimate challenge of creating more innovative and low-cost designs in the presence of more variation effects. TSMC drives this towards lower geometries, and more effects actually come into play because of the small geometries that are being used. They provide more capabilities to help engineers understand the manufacturability of their designs. Now, with the need for more extensive design validation, Solido offers efficient analysis capabilities across the PVT and Monte Carlo domains to give the most efficient validation across the variation effects that you see. This all cannot be completed without other EDA vendors involved in the flow, providing both an infrastructure and also the simulation engine to actually run the analysis. One example of collaboration, again within the TSMC OIP discussed by Jason, is the collaboration between Solido TSMC and Springsoft. Here, on the LDE side of things, we're actually working in developing the constraints that drive into the LDE API for working with back-end layout tools such as Springsoft to create a full interactive LDE-based development flow. Now Patrick Drennan of Solido at TSMC will be presenting a paper covering this technology that was being developed.